Welcome to Elektor Engineering Insights, the show that puts your engineering challenges to the industry's experts. I'm your host, Stuart Cording. Now, for most of us, cars are a mechanical marvel that have been a constant part of our lives. In fact, they're of such cultural importance that singers and bands from the Beatles to Janis Joplin have written entire songs about them. However, the reality is that vehicles are increasingly being defined by their software and accompanying electronics. One term on everybody's lips in the automotive industry is software-defined vehicles. But what does this mean exactly? What is the impact of those building cars, and how will they actually change? To answer these questions and more, my panel of experts this episode includes Eric Richter from Base Labs, Ralf Münzenberger from Incron, and Brian Carlson from NXP. Welcome to the show, everyone. I'm going to start with Eric. Just bring you in here. Hi there, Eric.
Nice to it.
Good to see you. Could you tell us briefly about yourself and your role at Base Labs?
Sure. Thank you for the opportunity. Yeah, my name is Eric Richter. I work at Base Labs, which is an automotive software company that develops algorithms that take in the tremendous amounts of data coming from all the sensors that we have in nowadays in future cars, like radars, cameras, and lidars. And those algorithms then turn the data or this data into reliable driving decisions for safe driving. That's what we do.
Fantastic. Well, thanks for that quick introduction. We'll come back to you shortly for a bit more of a one-on-one session and dig deeper into all of that. I'm just going to bring in, Ralf. I meant to bring in there. Hi, Ralf. Good to see you. How are you doing?
I'm fine. It's nice to see you, and thanks to be part of this webinar.
You're welcome. So what's your role at Incron, and what aspect of automotive is Incron focused on?
Yeah, I'm co-founder and CEO of Incron, and Incron is a tool provider as well as service provider for the design, optimization, and test of automotive ECUs, electronic control units. And we have a strong focus on the topic timing, and that's you see at our name. It's derived from the Greek god of time. It's Chronos, and it means to be in time or real-time capable. And without right timing, no car will drive from the yard.
Okay, well, good. We'll be finding out a little bit more about that shortly. And also Brian from NXP. Good to see you, Brian. How are you?
Hey, doing great. Thanks for inviting me.
You're welcome.
Exciting topic.
It is. And NXP is a very big organization. Where do you and your team fit in?
Sure. So I am Global Marketing Director for the automotive processing part of NXP, which is over 50% of our revenue. And NXP is the world's largest automotive processing vendor. So I take a look at it from the hardware perspective. But of course, you can't have hardware without software. So we provide more and more complete solutions and work with OEMs and tier 1s worldwide.
Super. Well, thanks very much for that quick introduction. I'm just going to provide a little bit more background around the way the show works, and we'll speak again shortly.
Okay, thanks.
Now, automotive electronics has been a constant in my life, from CAN-capable microcontrollers for airbags to discussing how Arduinos are used in developing a Rolls-Royce. So I have plenty of questions. However, this show is for you engineers out there struggling with such challenges. So, regardless of where you're watching, post your questions and comments during the show using the chat function on YouTube and LinkedIn. Or, if you use this too, Twitter using the hashtag ElektorEI, and we'll do our best to get answers or guide you to resources that might help during and throughout the show. Super, thanks very much. Let's come back to Eric. There we go. So Eric, Base Labs and talking about the topic of the software-defined car, I think is probably a good starting point just to understand where we've been in the past, sort of up until maybe 10 years ago. An electronic control unit, more commonly termed simply ECU, had a single function. So we might have a windscreen wiper ECU, a headlight ECU, and each of those ECUs had maybe one or two sensors, something like a rain sensor and an ambient light sensor. How is the electrical electronic architecture, also known as EE architecture, changing, and what's driving that change?
Yeah, that's a highly relevant question. So indeed, in the past, we only had those ECUs that had a single function. But I would say it's also important to understand that those sensors that you mentioned, like rain sensors, they had, let's say, very small amount of data only. So they had an individual signal, maybe giving an indication whether it's raining or not, or what's the amount of rain. That's all. So I think we have two major things that drive this change. This is on the one side, the huge amount of data that the new sensors are bringing, like the cameras. Imagine high resolution camera images. Imagine radar sensors that have lots of detections that they are providing, and LiDAR sensors, of course, they also provide lots of data points that need to be transferred over the wire. So that's a really technical challenge. The bandwidth, or the device is the bandwidth question in the car. But the second thing which drives that change is that those new sensors, they all perceive the environment of the car, and they want to understand which other traffic participants are out there, and that's really the new thing. And for that we need processing, a lot of processing power and algorithms. And I would say those two things that drive that change, and also introduce things like new domain controllers, high performance computing, and all these things.
Now that's an interesting point you make there about this change to different architectures, and as you said, the sensors are very varied. They're different sizes. They have different amounts of data that they're delivering, and they're delivering it at different sampling rates. But I think one of the other things we're seeing as well is that a single sensor is actually going to be used by more than one ECU, and that's a change from the way these automotive systems have been built in the past. Is that right?
Yeah, definitely. And although we always talk about a single sensor like a radar, especially if that sensor is used by multiple ECUs, as you said, then typically we also see that those multiple ECUs have different requirements towards the sensor. So it might be that one ECU requires a specific data format from that sensor, and a specific data level even, and another ECU may require another data format from the very same sensor, or even data at a different level. So this makes it really much more complex than in previous architectures, I would say.
And so what are the challenges that arise because of that? Because we've got now maybe one sensor at the front of the car, like you said, a radar, but that now needs to provide that data to multiple ECUs within the vehicle, because they're all using that information for different things.
Yeah, I mean, if you talk about these ECUs and those requirements, then we always have the question, how much processing also happens on the sensor side?
Right.
And this also has influences to the bandwidth that is then required. There are driving functions that have, let's say, lower requirements to the amount of data that such a sensor is providing. So more pre-processing or processing can take place on the sensor, but which also increases the processing power that is required on sensor side. We have other driving functions or ECUs that tell, or that want to have the data at a more lower level, for instance, which requires less pre-processing on the sensor side, but more pre-processing on such a, let's say, central processing unit, for instance. And those things, they have to be combined, and they have to be present at the same system, the same car. So I would say that's one of the challenges that we definitely see, deciding on which level those sensors provide their data, how much pre-processing occurs on which side. And that's kind of a wave. It's also kind of going through the industry with time, kind of. So we see that this also changes. And in one year, let's say, a lot of pre-processing takes place in the sensor side. And another year, OEMs and maybe even suppliers want to have more processing in the central ECU side. So it's really kind of a wave in the industry.
So the data from these sensors is being brought together, and it's a term, the process is normally termed fusing, so data fusion, and that sort of brings it into a sort of homogeneous form that can be used by the ECU. How is that implemented?
Yeah, that's a tough one. So actually, if we talk about fusing or sensor fusion, which is also a commonly used term there, then I would say it's rather an umbrella term for a bunch of algorithms and techniques that are out there, that are already existent or present since years or even decades, but also algorithms that are currently heavily under development. So and there are different reasons for doing or because or why we are doing sensor fusion. One typical reason is that you want to reduce things like sensor noise. So think of a radar, for instance, that provides a distance measurement and an angle measurement of an object that is in front of the car. Then typically the radar provides highly accurate distance measurements, but it's not that good in observing the angle or the lateral position of an object. So now you can add a second sensor with opposite properties like a camera, which is good in observing the angle or lateral position, but it's not that good in measuring or observing the distance of an object. So if you combine those sensors, then in theory you get best of both worlds, and that's what sensor fusion is doing. That's one reason why we do this, combining the strengths of two sensors in terms of measurement noise and sensor errors. But another very important aspect or reason why we're doing sensor fusion is that you want to increase availability. So it might be that one sensor detects an object, but the other one does not. And by combining those two sensors, you can increase the availability of the system. And the last and the third very important reason is reducing false alarms. It's very often not very likely that the sensor reports an object, but actually there's no object at all there. And the other one can, let's say, reduce this false alarm rate. That's the third reason. And depending which of those things you are addressing in your system, the resulting algorithm can differ. But at the end, all of those algorithms, they typically address all of these aspects at once with, let's say, different weights of these aspects.
Yeah. So where's the sensor fusion actually deployed? Can it be deployed in the sensors, or is it typically deployed then in the ECU, or maybe do we have several sensors connected to an electrical system, to a sub ECU that then fuses the data together and then parses it in a common format to a domain controller or an HPC?
All of the options are valid and all of the options are done at the moment in the industry. So we see sensors that do sensor fusion inside the sensor. For instance, there are camera sensors where you can directly connect a radar, an additional radar sensor to the camera sensor. And then the camera is kind of the master, also the master processing unit. Also, the opposite or vice versa is also possible. You have the radar as the master and get some data from the camera. That's an option. But last time, more and more, also OEMs want to do this centrally. So sensors just provide their data at certain levels, and then the sensor fusion is taking place on a central processing unit. This is also because the lower the data level gets, the more processing power you need. And then, at least for modern systems and higher automation systems, you really need much more processing power in terms of a CPU or even GPUs, depending on the system that you have in mind.
Now, obviously, we're seeing a lot of new sensors in the vehicle compared to a decade ago. There's short range and long range sensors. You've mentioned cameras already as well, and all these are being used for advanced safety systems, and even there's a looking towards implementing autonomous driving. Those sensors, what sort of information do those sensors deliver? How much is the information already processed by the time it comes into the sensor fusion software block?
Yeah. Although there we see a wide range of options in the industry, and I wouldn't say there is a standard yet established. For instance, look at the camera sensor. There we have what is typically called smart sensors that provide a list of objects. For instance, where each of those objects in the list consists of position, velocity, driving direction, acceleration, length, width, those properties on an object level. That's a very typical approach that we also see for the ADAS that we have in the market today. But staying on the camera side, newer system, they cannot really work with that level of data on the object lists. They, for instance, require to get the images directly with some semantic label attached to each of those pixels. And you can imagine that this increases the amount of data a lot, but also increases the information that it's still in the data. And the more you go to higher levels of automation, the more data or the more information about the environment you need. And this drives this data level going towards lower levels. Yeah, it's a similar thing for radars. In the past, we saw a lot of smart radars. Again, they provided a list of objects, each of those objects with position, driving direction, velocity, and so on. Newer systems, they go one level below that, where you get detections. So which also means that for a single object, you may get multiple points along the car, for instance, on the road. And this is then called high resolution radar, where you get hundreds of those points. And if you go to LiDAR, then you get thousands or tens of thousands or even 100,000 of points of the vehicle's surrounding per shot, per cycle, which means if you have a sensor at 20 milliseconds update rate, then you get this 50 times a second. So a lot of data is coming and need to be processed.
And so when the data's coming in, how is the Base Lab solution presenting that data to the systems that are in the vehicle so that they can make an intelligent decision? Because obviously this is a safety critical functionality in many cases for guiding the vehicle, getting it in lane, or maybe making a decision as to whether to brake promptly because there's a pending accident about to happen.
Yeah, that definitely. Again, this depends on the driving function, and there are different levels for that output as well. So if you look at today's ADAS functionalities, then typically customers request us to provide lists of objects again. So then in the simplest case, lots of lists go in to such an algorithm from Base Labs, and again, a list of object gets out, but with better properties, higher accuracy, less false alarms, and maybe an even higher detection rate or availability. So all the things that come with sensor fusion, they also come at that level. There are other customers and driving functions that need the output of such a sensor fusion at a lower level. For instance, there we provide an output on what we call a cell level, right, where you have the world discretized in a bunch of cells, tens or hundred thousands of such cells, and where each cell represents whether this region is occupied by an object or not. And if it's occupied by an object, what's the speed or the velocity of that object, and what's the driving direction, once again. But it's at a lower level where the Base Lab software, for instance, didn't decide which of those cells build an object or not. This then comes at a later stage on the customer side. And there are driving functions that never require that an object representation has been built. They always operate on such lower levels.
So obviously a big part of this move towards software-defined vehicles is that now we're making software responsible for our safety, and I mean that's something that the aerospace industry has been tackling for decades already. But obviously, there's a significantly smaller number of aircraft flying around in comparison to the number of vehicles on the road under completely different conditions. So, how does a company like Base Labs ensure the quality of software, which is essentially a framework? You don't know as you're developing this framework how it's going to be used and necessarily which sensors are going to be attached in every possible use case, and therefore to ensure the safety of the software that's being put into these systems.
Yeah, that's a highly relevant question. So at the end, for at least some of the aspects, we do it very similarly to the other industry that are in the market since decades. So following standards development and processes or standards according or that relate to the processes how you develop the software. In automotive industry, the most common standard is the ISO 26262 for functional safety. That's something that we follow. Our software is also certified according to that standard, up to a safety level or rating of ASIL B. So you probably know there are 4 of these ratings from A to D, and B is the one we got certified for our software. So we follow those standards. Also things like ASPICE development processes, which are well-established processes. And then, of course, we are doing tests a lot. And I mean, this is a topic by itself, and of course we are doing the things that have to be done, testing with simulated data, so artificial data, but also testing with customer data. So in fact, most of the data that we have and that we use for testing is coming from our customers, from real vehicles with real sensor setups, because at the end, the edge cases that they are hard to find using simulated data only. At the end, you need the data from the real scenarios, from the real world, and our approach is taking the data from the customers, putting them into the software, and then testing whether it's doing the right things.
Super. Well, thanks very much for providing that insight into sensor fusion and also the new range of sensors and how they're being integrated into the automotive mix. We'll come back and get you to provide some comments and thoughts on some other questions as well when we do the roundtable session at the end. Thanks very much.
Sure. You're welcome.
Super. So I'll come over now to Ralf. Welcome back, Ralf.
Thanks a lot.
So where I wanted to start with you is that software has been a growing part of the automotive mix since the 1970s. But despite the fact that software has been around for years and years, for decades, we still hear in the news that cars are being recalled for firmware updates. Why is it that sort of automotive manufacturers are still struggling with software development?
It's a very tricky and complex question because there are many, many aspects. But let me focus. I'm now in the automotive industry for more than 15 years, and I see a big change. The mentality was more of the mechanical industry. Yeah? It was focusing about the shapes and all these things, the mechanics. And now the software is playing a more and more dominant role. Why? Because it's driven by ADAS, autonomous driving, electrification, car-to-car communication, car-to-cloud communication, all these things. And the value added is mostly or more and more on the software. That means the software is increasing exponentially. To get you a number, in a premium car today, it's about 5 times more lines of codes than in the Boeing 785 Dreamliner.
Wow.
That's one.
Okay.
That means we have a software complexity increase, as well as we have an increase of the project size, the members, as well we have a technology complexity increase. Yeah? More and more complex ECUs, SoCs with a lot of cores, a lot of hardware accelerators, I mean, for example, provided by NXP, is coming up. And therefore, we have to rethink the development process.
Okay, so I mean, I think many people who've sort of worked on embedded software development have maybe focused on a single microcontroller for a single application, something like a coffee machine or maybe a PLC in the industrial space. But what's amazed me over the years is how complex the software development process is in automotive. Maybe you could please describe how many companies are involved in software development for an automotive application today, and how it's all layered.
It depends on really the domain and the electronic control unit itself. Sometimes it's provided by only one company, and the software is coming by one company mainly, or the application software, and maybe the middleware coming from another one. But that's not the very interesting projects and where it's very complex. But if you go to something like a domain controller or an HPC, there are today's it's coming the software from 2030 different companies. They are providing software provider, and we have as well more and more that they are coming from different domains inside. That's also increasing the complexity with a different philosophy about architectural design. That means it's also increasing the team size in overall. Where they 10 years ago it was maybe about 50 and 100 people. Now in a complex ADAS system, domain controller ADAS system, it's about several thousand people are working on such a project.
Wow. Okay. So, I mean, that must make a lot of challenges as the automotive OEMs, the original equipment manufacturers like BMW and VW and Ford are trying to push their vision into the vehicle, because the automotive industry, they're changing the architecture of the car, aren't they? They're taking away these individual ECUs, and they're building up a big network of domain controllers or zonal controllers, and introducing these high performance computers or HPCs. So who's driving this move forward with software development?
I mean, first of all, we had this with Tesla, and they have the central control unit, and they have done it in this way and putting a lot of software onto this electric control unit. But on the other side, we have now in a premium car more than 150 of such technical computers, ECUs. Right. And I mean, that's really very hard to handle. And though there is a centralization going on since years, maybe 2, 3, 4, it depends on the company, central ECUs. On the other side, there are the zone controllers as well. They are more connected to the I/O, to the sensors, the actuators, and the brains are the central ECUs. And that's causing, from an OEM perspective, and a system architecture and system integration perspective, it's really very hard, because you have a decoupling of the sensors from the actuators. That means the latencies are getting longer and longer between the sensor. For example, you have, as Eric mentioned before, you have a radar system or you have a camera system, and you have the sensor data fusion. And you have longer latency, and that everything has to work perfectly together.
Exactly. Now, you mentioned the word timing there, and of course that brings us back to the company Incron, which is based on Chronos, as you said, the Greek god of time. Yeah. Now, if I were to look at the industry, the automotive industry, from as an outsider, you would think timing would be a central pillar of everything they do. I mean, when I brake, for example, I need a certain stopping distance, and that's all dependent. That's all measured in time as well, reaction times and passing data. So, why is it that the automotive industry needs help in tackling these timing challenges and latency issues?
Yeah, if you look to timing in a braking system or electrical steering system, I mean, that's obvious that time is important. You brake a pedal, and then after a certain time, you have to de-accelerate. And inside the ECUs, there are the algorithm every 10 milliseconds are executed. I mean, that's where it's obvious. But for a complex ADAS system, for example, emergency braking system, there is an end-to-end latency between an obstacle occurs on the one side and the deaccelerating starts. It's about 380 milliseconds. That's
right.
2 blinks of the eyes. Yeah, it's fast. I mean, it's not a lot of time, and that have to work perfectly together. And you have sensors. You have a sensor. First, for the sensors, you have an ECU. You have buses like CAN or Ethernet, maybe FlexRay inside. You have a central ECU. You have an ECU for the braking system and the electrical control units. So there are around 5 to 15 ECUs involved in such an ADAS systems. And they have to, again, to work perfectly together. You have time critical data paths, like I've mentioned before, with the 380 millisecond, and that's going over all the buses, the ECUs, and that has to be designed. That has to be planned at the beginning, who gets which part of the latency and budgets. That's what we are doing with our customers, and we are providing simulation tools as well as trace analysis tools for such data path analysis, or we call it event chain analysis. Right. And that's getting more and more important because it's now, you can say, with ADAS system today, maybe there are about 50 time critical event chains on a car or vehicle level, and that's growing up to several hundreds in the future for autonomous driving systems.
So at what stage in the development process can Incron help? Is it more during the testing stage at the end of the project, or are you more focused at the beginning when the system architecture is being defined?
Yeah. First of all, I'll give the answer. I've never seen a project which starts too early with this timing and event chain analysis. But what is very important is to start already with a model-based during requirement analysis with a model-based approach. That means you really specify your requirements precise, and you negotiate also the requirements between different partners, especially when it comes to such data paths. And then for sure, at latest, you have to start, in my opinion, during the design phase, because if you have a system, or what we see many times in the companies, you have firefighting jobs at the end of the or short before the SOP. There's something struggling in the left corner. Yeah, if you're leaving the interstate here, and they think it's a functional problem, but it seems we see such sporadic errors are typically timing problems or event chain issues. And that's why if you have a resultant or a robust architecture, that will not appear later on.
Super. Well, thanks very much for that introduction to the topic of timing and the growing complexity of the automotive systems. Stay with us. We'll have you back in again at the end for our round table. And I'm just going to take a break here at this point to say thank you very much to our viewers. So before I move on to Brian, what I'd like to do is introduce our giveaway for this show and a little bit of thanks from my side for supporting us. So this time we have 9 copies of the ebook Controller Area Network Projects with ARM and Arduino available. This has been written by Dogan Ibrahim, and it covers everything from the basics of the CAN protocol and its error detection mechanisms to using CAN in conjunction with boards based on the Arduino format. Now, if you'd like to take part, use the link below and enter the keyword e-mobility with your entry. And I wish you all the luck with that. So without further ado, we move to our final guest, Brian Carlson from NXP. Welcome back.
Thank you.
So NXP at Embedded World introduced a new series of real-time processors, the S32 family, and that's a family squarely targeting automotive with some really impressive statistics. Can you tell us a bit more about the family and also a little bit more about the manufacturing processes, silicon process technology node that they're being manufactured on?
Yeah, sure. So we introduced the S32 family. Actually, prior, we introduced specifically at Embedded World, and we won the Best in Show hardware award for the S32Z and S32E processors, which are real-time processors. So the S32 platform has a range of processors that work at the lowest levels. We're talking about sensor data, radar sensors, to the highest levels for vehicle compute, central compute, and also at the end nodes for those windshield wipers, the motors, the heater. So we have a full range of devices. So where we really focused here at Embedded World with the S32Z and E is addressing these new architectures, right? They're data-driven, they're software-defined, and that has a lot of implications. This is not the old world of one box per function, an ECU that just does one function. It just has a microcontroller inside. So what we introduced is a 16 nanometer device. It has 8 Cortex R52 cores, a lot of peripherals, DSP, machine learning, high-speed gigabit Ethernet, and support for this new world of software-defined vehicles. In this new world, you need to be able to run multiple applications simultaneously. A great case, what we showed is for an electric vehicle. I have to do battery management. I have to do energy management. I have to do power conversion, onboard charging, DC to DC. I need to control the vehicle, real-time control. Traditionally, that would take 6 different boxes. So what we do is converge all those functions into a chip. So it's very representative of where the market is going with software-defined vehicles. One chip now can do multiple functions that previously took multiple ECUs, and that requires a new level of technology. Of course, we talked about safety. You need ASIL D safety, right? You need security. That's something we haven't talked a lot about yet, is security, because the vehicles now are connected to the cloud. There are various hacking attempts even within the vehicles today. So security and safety are fundamental to that, as well as virtualization of the hardware. So they're totally isolated. I can have functions from 5 different tier 1s running on the same chip. They have their own memory, their own peripherals, their own IOs, and they can't interfere with each other, and have guaranteed bandwidth. That's a revolutionary, that's a new way of designing chips. And that's what we introduced at Embedded World in June.
So hypervisors are something that's more common in sort of servers, and maybe some people have had experience running a second operating system on the operating system that's already on their PC. Could you just explain briefly what is a hypervisor and how that sort of benefits software developers?
Yeah, so it's 2 levels. The actual hardware itself, that's what's unique, is that you don't necessarily have to have a hypervisor, because now the hardware builds in that technology. And what a hypervisor does is typically allow you to share the same hardware, whether it's the same core or the peripherals, in an abstracted way. So I could write a software task, or say I'm running an application in the vehicle, and I want to run another application that shares resources. That hypervisor is a software layer that manages those 2 functions and allows it to have access to specific peripherals. What we did in the hardware is actually take that capability and build it into the hardware. So you could have those 8 cores, for example, run individual functions, as I talked about, that are totally isolated in hardware. There's no software required for that. And we've shown where we run, in one example, we show 4 AUTOSAR machines running a free RTOS machine and 3 bare metal machines across those 8. Now, where a software hypervisor does come in is valuable is when you run multiple OSs or multiple applications on the same processor. So you could have 8 processors discretely running totally isolated, or run a hypervisor across those and have even more functions that are isolated at another level with a software hypervisor. So there's different levels, and different people take different approaches. At the end of the day, you're trying to put a lot more functionality on the same hardware, whether it's through hardware isolation or through software virtualization or through a hypervisor.
So this means that with a hypervisor running on the S32, I can actually execute different applications with different functional safety levels, everything maybe from as high as SLD right down to maybe quality assured level, and there's no way of those interfering with one another. Now, in a typical hypervisor, part of the hypervisor's job is to share all of the hardware interfaces amongst all of the operating systems that are running. But I understand on the S32, family on the E and the Z, there's actually a pin-to-core capability as part of the hypervisor hardware support. Could you cover how that works?
Yeah, that's a really important. I think that's one of the key innovations. There's a few key ones within this device, but that was probably the most important because it was designed for software-defined vehicles. Really, it may be one of the first devices designed to do that because it does have what we call core-to-pin isolation, which means we can actually lock down from the core to memory to peripherals all the way out to the I/O pins, and actually allocate I/O bandwidth, memory bandwidth, so there is a specific environment that application is running in. Effectively, what the software will see is exactly what it would see in a normal environment today, right? It's an isolated box with its own memory, its own peripheral. It has total control. It's isolated from the rest of the world through interfaces. Yeah. So we've basically taken the old world of discrete boxes into the new world with virtual ECUs by leveraging that core to pin technology. And then, like I said, you can layer on top of that even software virtualization or hypervisors on top of those environments also. But that's the key, is the true hardware isolation within this device.
Now, there's also an incredible amount of connectivity on these devices. We've got the sort of automotive Ethernet capable communication block, but then there's also a separate block just for CAN interfacing. You've got, I think, 24 CAN interfaces and 2 dedicated Cortex processors just for CAN connectivity. How does that all play into the mix and the capabilities and applications that this technology can target?
Yeah, great question. And actually, this goes back to the S32G processor, which we announced last year, or which we went to production with last year. What we found from the OEMs is the amount of data. We're talking about all the sensor data, the great conversation we had with Eric about all the sensor data. But there's a lot of data within the vehicle. We're moving to gigabit and 2.5 and ultimately to 10 gigabit Ethernet in the car. There's lots of traffic. The CAN is moving from gigabit to faster. We now have from a megabit to 5 megabit to 8 megabit and now 10 megabit CAN with CAN XL. You can't process all that effectively with microcontrollers. You have to offload that with a data offload engine. So this is the value that NXP has been providing, starting with the G for gateways, extending that technology into the domain or zonal processors like the Z and E, which allows us now to have 24 CAN interfaces that come into the chip and can be totally offloaded. So I can do a lot of intelligence directly on those streams. I can mirror the CAN traffic. I can send CAN traffic to multiple ECUs in parallel. I can route CAN traffic to Ethernet and actually packetize and go off to the Ethernet. On the Ethernet side, the move to gigabit Ethernet is huge, right? As we move to these zonal architectures, we're moving data low latency with time-sensitive networking and gigabit Ethernet. We need a way to effectively move traffic within those zones, and these processors have that built in. So there's actually a NetC IP, which allows us to virtualize, as we talked about. I can have multiple tasks. I can have 8 tasks with their own IP addresses. So it really takes hardware to the next level for software-defined vehicles because it's truly virtualized in hardware. And from a software point of view, it's beautiful because they write their software as they would in the past as a discrete ECU. But in reality, it's multiple things running in the same processor, and they don't know about anyone else that's running on that processor, which is exciting.
It sounds incredible, and it also seems like the sensible way forward for the automotive industry. I mean, having looked at the vehicles for years and worked with some of the tier 1, tier 2 suppliers into that business, you've been scratching your head for a long time thinking, why is this all independent? Why don't you just pack it all in? And this is a nice way of pulling all that together. But I think one of the thing that comes out clearly, speaking to all of you today, has been how complex the software development is becoming. So how is NXP supporting automotive software development?
Yeah, it's a great question because in the past, silicon vendors provided a chip, maybe a board support package or drivers, and said, there it is, tier 1, develop the box. The box delivers the tier 1 delivers a box to the OEM. And that's not the way the world works anymore. As we are moving to software defined. And by the way, with all that the sensor data we talked about, we work closely with cloud service providers too. So now there's the cloud equation of how that brings together. So NXP is really focused way beyond the silicon into the complete software stack, the security, working with cloud service providers and enabling things like containerization, so you could actually deploy services much like a data center to the vehicle within the chip. So software is very, very critical, having an ecosystem all the way from the low-level types of applications within AUTOSAR environments to middleware, moving data like DDS, sharing data, AUTOSAR, adaptive environments, all the way up to vehicle health prognostic applications, over-the-air update applications, intrusion detection. Software is critical to all of this, and it's requiring not just the low-level software, but all the software all the way to the cloud. And as we go forward, software-defined vehicles, it really changes the way that these automobiles are designed, because now you have what's called a continuous improvement, continuous development, continuous deployment, or CI/CD. So basically it's almost like an agile process where the vehicle is going to get more intelligent over time. Smart data is smartly acquired within the vehicle, brought to the cloud, run into digital twins, machine learning, deploy new updates to that vehicle continuously, so that perception we talked about, the fusion algorithms, those get better over time. The electric vehicle, the energy management and the battery management gets better over time, so your battery lives longer, it has farther range over time, and the ultimate experience gets better. But all of that requires software from the bottom of that chip all the way to the cloud, and those interacting is very, very important.
Well, I think we could probably have a chat for another half an hour on the details. I think it's a fascinating product, and be very exciting to see where it's deployed and what difference it makes to the user experience in the automotive space. So thank you for your insights on the S32 from NXP.
Thank you.
So I'm just going to bring in everybody else so as we can have a bit of a round table discussion. As you can imagine, there's quite a lot of chat going on. So I'm just going to look through some of the questions that we've got. I think maybe one of the first questions that we should tackle is, we talked about EE architectures, electronic architectures, and they're changing, and that describes, let's say, the network of boxes that are going to be deployed into the vehicle. There's two different approaches that seem to be out there. There's a domain architecture, and that seems to be splitting the vehicle into its domains, which are sort of typically the drive chain, the body electronics, for example, sort of comfort features and things like this. And there's another approach which is the zonal architecture, and that seems to be saying, well, I'll put the electronics near where the sensors are, and we'll deploy the functionality across all the boxes supported by these highest performance computers. Is that how it's actually happening? Are we seeing a strict, we're going down the domain path versus we're going down the zonal path, or is it a bit mixed, or is it still a little bit unclear as to which way we're going in the automotive industry?
I can take that first, probably because we're already dealing with the OEMs globally on all these architectures, and I actually have some slides if people are interested to engage. I have slides that kind of show there's a progression, and it depends on the region. It depends on the, and actually I will move to another slide that actually gives a little bit of insight, but I have probably a better slide. As we go to this kind of flat architecture, we have been seeing domain architectures evolving already. There are new platforms that are going to production now that are domain. I would say globally, by start of production 2025 and beyond, we see the leading OEMs moving very aggressively. And this is not just a Germany thing. It's not just Europe. It's worldwide. Right. Whether it's China, US, worldwide, there's a lot of competition now in the world. And we see the zonal architecture. It's almost like something happened because of the supply chain, because of COVID. Things are moving very, very quickly. It's becoming more and more competitive. So we see SOP 25, a lot of these zonal architectures come to fruition. So between 2025, 2027, we do see those coming in as we go from flat to either domain or zonal. And there's hybrid. There's people that'll do domains for the body maybe, but then zonalize the rest of the vehicle. So it's moving very quickly.
What about you, Eric? You're obviously at the sensor end mostly of these changes. How is the market changing from what you're seeing?
Well, on the one side, I see a change in the use cases that we currently address in the community. While in the past we majorly talked about for privately owned cars, it completely, or I would say, it heavily changes towards also commercial vehicles, so and higher levels of automation that will appear first in commercial vehicles, probably even in fenced areas like logistics centers or hubs, things like that. Because that's from a technology side, it's less complex on the one side, but also from a business case side, they seem to be clearer, at least at the moment. What's the benefit when buying such a system?
Yeah.
But coming back to the also to the zones question, for us, major question is, will there be, let's say, strong efforts in going to much lower levels of data coming over the buses for doing things like sensor fusion, or will we see again systems that do more processing on the sensor side?
Right.
Because there's also companies that are doing such things still. So I wouldn't say there's one direction for the whole market. It's still a lot of diversity inside, I would say.
Thanks. So I think one of the other questions, or a topic that's come up a few times in the questions that we've got here, is around the aspect of security. Obviously, we've seen many different types of hacks on cars over the last 10 years, from the key fob just to get into the vehicle, to be able to actually completely drive it away, or even remotely control it when that sort of control aspect is part of the system. Ralf, do you think that the topic of security is really being addressed in the automotive industry as in the projects you're seeing? Is it front and foremost, or are we still figuring it out how to approach it?
I mean, I see it at the OEM side. They are really addressing the security topic because it's very important here. On the one side, it's again what also Brian mentioned. It's the car to cloud communication. Yeah, that's very important. But also the hacks from outside, and we have seen a lot of hacks. I mean, they are going through the press and all these things. I think they are addressing it, but on my perspective, from the timing perspective, there's an important point, because when you bring more security into a car, or you can say into an ECU, it takes time and performance, and it takes also some memory bandwidth, yeah, as well. Yeah. And that's something I will say is more the problem than the concepts. I mean, they are familiar. They have working groups, task groups they're working on. But if it comes to a good architecture and really about more with the power you need in an ECU, and also that's sometimes something that it's underestimated what it means.
So, Brian, this is also security is another sort of cornerstone of the NXP offering. I know you're very active in that space. I mean, are we at the point now where, I mean, we know that security has been breached over CAN buses just because the data flows and there's no encryption at all? Are you seeing that that the data over CAN is being encrypted, and is security part of the silicon?
Yeah, so security definitely is top of mind. It's designed in. When we do our silicon, it's designed to the ISO SAE 21434. In fact, we got certified last year from that. Right. Security is end to end, right? And you talked about CAN. CAN is one of the weak areas, right? CAN didn't have any concept of security. We actually developed, pin for pin plug-in secure CAN transceivers now. So there are mechanisms to be transparent to existing designs that you can plug in secure CAN. But you talked about performance and the impact of performance. Yes, that is an issue for the older processors. The newer processors, what we do today, now have an integrated hardware security engine, and it's much like a secure element, right? The technology that NXP has been doing within bank cards, within your passport, it has that technology. So we're leveraging that technology now into automotive. So I think the performance side of that is managed now by hardware accelerators that do that, offload that task. And then the CAN buses can be managed through transceivers that plug in secure CAN transceivers. But it goes way beyond, as we talked about. It's end-to-end. You have to have secure communications to the cloud, leveraging encryption, leveraging authentication, and leveraging other techniques, and also tamper resistance and attacks against. There's a lot of hardware out there that do attacks against secure chips. So you have to have methodologies in your silicon that work against those types of attacks also. So it's a pretty complex topic. Yeah,
exactly.
So I would like to add.
Yes.
Something there. For sure, we have lots of, let's say, attacks that, let's say, follow a rather, let's say, classical approach where a hacker really goes into the car and does something with the machine. But from a processing perspective, there is another form of attack using, for instance, adversarial images, where for instance, a simple sticker on a traffic sign can influence what a camera sees and how it perceives the environment, and it may detect an object, although there's nothing. And I would say those kinds of attacks, they are pretty hard to, let's say, to tackle with the things that you mentioned, Brian and Ralf. From our perspective, Baselabs would say, well, you have to use sensor fusion and another sensor for bringing in diversity into the system, using another measurement principle, which is not which cannot be attacked by the same attack at least. This also helps to increase the security, although it can't be seen as a, let's say, classical hack, but actually it is a hack.
Yeah,
exactly.
Sign hacking. There is
exactly.
hacking.
I was going to say, because we've seen examples, I've seen scientific papers on this topic where a label has been put over on a speed camera, a speed sign, for example, and it's suddenly disappeared. So do you think to combat that we'll see diversity of machine learning algorithms? So there'll be maybe two algorithms deployed assessing the camera information in order that there's an alternative opinion as to what the road sign was.
Any diversity helps for sure, and there might be a valid approach using multiple ML or machine learning instances inside that have been trained differently. But of course, using another sensor and another sensor modality is also an option. And as always, also in automotive, we have lots of different options.
And that gives.
But I would say using a second sensor or second sensor modality also helps for other situations, not inside of an attack, but just in normal mode. So that's why I would expect to have multiple sensor modes in the car, anyways.
And of course, that gives Ralf's team something to do as well, because that will have to be packed into the timing planning and the event chains. So okay, I'm just going back to the questions again and to have a look here. So a lot of discussion about sort of examples of autonomous driving. Just a general question here that I read earlier was, so when it comes to autonomous vehicles, I mean, Tesla seems to be right at the sort of like at the forefront there of what's possible for consumers to use on our streets. Do you think we're going to see fully autonomous vehicles available to be purchased by the public and used on a day-to-day basis? And if so, sort of what sort of time frame do you think that's going to come?
I mean, if we talk about autonomous driving, we always have to talk about the level of autonomous here. I mean, if you have a second level, that means you needs to have your arm or your hands on your wheel, and have to drive by yourself. And only if you go to level 3, then you can have your eyes from the street for a certain time, and maybe there's some warning. That's first of all. We have to talk about what. And Tesla at the moment is level 2, for sure, and not for level 3 or 4. And you cannot go to the back seat and let your car drive.
Play on your Game Boy.
I think for level 3 or 4, we will see in the next 10 years, is my estimation. I mean, there's a lot of going on in discussion, and we're talking about years when it will happen. Yeah? But I think there will be a shift, and it's good because it will be more safe, and it will be save lives as well. And maybe when I'm an old man, I can drive anymore with an autonomous driving car. And I was part of this show with the development. So I think it's going to this direction, but the question is, it's very expensive to develop such a system. And I think there will be a more concentrating between the OEMs, or it's needed because they are doing all the same, many, many times. And that's where no one want to pay you if you buy a car. And that's it's a very important issue to collaborate and to have good, like sensor data fusion or other algorithm, which can be shared by many suppliers.
Yeah. So my prediction would be that we will see automated vehicles within the next years. But as I already mentioned, my prediction would be that we will see them in commercial vehicles. We will see them in fenced areas.
Yeah.
That's for sure. The business cases are clear, and the benefit, also the complexity is low there. I have some doubts that we will see unsupervised automation or level 4 automation in privately owned cars in the next 10 years. I have some doubts on that. Might be a different thing for shared mobility providers, but for privately owned cars, the business case is really tough, I would say.
How's it look from your side then, Brian, from the semiconductor aspect of and the customers you talk to?
Yeah, no, I concur. I think where we're seeing a lot of the momentum around autonomy right now is around the commercial vehicle, like long haul trucks, where a more controlled environment, that we see a lot of customers doing that successfully today. Controlled environments, shared mobility type applications, but not generally autonomous drive. I would say if you look at the investments, tens of billions of dollars per OEM is in EVs. I think the EV is the focus, right? It's hitting the 50% by 2030. I think that's accelerating. And you got to start to think, because you can't put 2,000 watts of processing in the back of an electric vehicle, because now you lose the range of electric vehicle. I don't think people are thinking about that, right? As much as they should be, right? So you got to balance that. What's more important right now? I think at the end of the day, I think you made a good comment, Ralf, that it's about the safety, right? I think we're going to get better and better ADAS features, more and more autonomous. The emergency, the AEB, and these types of things are saving lives already. I think that's where the focus is going to be, and you won't see L4, L5 for quite a while. And if you look at the market for that, it's very small until years out, right? So the focus is in making things more safe, and then specific applications. Look at agriculture, look at mining, look at very controlled environments and long haul trucking. Things like that have applications we're seeing today using autonomy, right?
So we're rapidly coming towards the end of the show, and obviously it's lovely to have this discussion. So I'm just going to pop in one last question from the crowd here, just to maybe nail down a bit more the aspect of software-defined vehicles. When do we think software-defined vehicles, as we've been talking about them today, and as has been proposed by most of the big OEMs, when are we really going to be able to buy one of those and drive it on the street? Maybe Brian first on that.
Yeah, those are in development. So like I was saying, where we start to see those come in with these new architectures too, it all kind of is a package deal. Really start to see that in 2025, 2026, 2027. The initial ones will start coming. And the beauty of it is they have a whole life of their own, right? They'll get better and better over time. They're designed to be upgraded through a decade of software updates. So that's the beauty of it, is that it's not just a one and done. It's something that vehicle will evolve over time, right?
And Ralf, is that also what you're seeing?
I think as well. I mean, the question is, what is really a software-defined car which will be on the streets here? And that's not a very hard definition, first of all, here. Though it will be more focus on the software, and that's already under development, and it will come in the next years more and more and more. And I mean, again, it's software-defined car is for me not a buzzword. It's really a change of mentality, and it's that software is really with a main part of the car, and it's and that will come is today, but it will be more and more important in the next years.
And a final word from Eric.
Well, nothing to add here. Share the opinions of Brian and Ralf, actually. Yeah.
Yeah, and that will obviously mean plenty of sensor fusion applications as well to keep that automotive industry safe on the roads and capable of implementing ADAS and autonomous driving.
Yeah, definitely. Definitely.
Super. Well, thank you ever so much for all of your contributions and your inputs to the topic of software-defined vehicles today. I'm just going to take you out and just do a quick wrap-up at the end here. So thank you for joining us.
Thank you, Stuart.
So the world of automotive is changing. Mechanical engineers will still have plenty to do, but much of how the vehicle drives and what we experience inside it will depend on software developers, electronics engineers, and semiconductors. And my feeling is we're still just at the beginning of this change. So if this excites you, now is the time to jump into the world of software-defined vehicles. Thanks to my experts today, Eric Richter from Base Labs, Ralf Münzenberger from Incron, and Brian Carlson from NXP. You've delivered us some brilliant insights today. So that just about wraps it up. Please like, subscribe to Elektor TV on YouTube and share our videos on whatever platforms you use. Or drop by the website at elektormagazine.com/Elektor Engineering Insights to see the topics for future shows. And if you'd like to join me as a guest, write me an email, drop me a tweet, or reach out to me, Stuart Cording, on LinkedIn. Thanks for joining, stay in touch, and don't forget to keep asking your engineering questions.